Well, good morning, everyone. Just to give you a little bit of information about how YouTube live stream works that's a little bit different than Zoom is that there's about a 10 to 20 second delay between what you see on the screen and what I'm doing and what happens in the chat and that sort of stuff. So it's not quite as give and take as it would be for a Zoom meeting or something like this. But the value of this particular format is that you can, or is that I can upload it extremely quickly, and it doesn't take a huge amount of resources like it does to upload a Zoom, a recording of a Zoom. So that's why I like to do YouTube live streams as well. The other thing is, I think that mainly takes care of it. So it's kind of nice, but hopefully you'll feel free to ask questions in the chat. I'm going to discuss a little bit about what I talked about in the lectures for this week, earlier part of this week, for yesterday's lecture and today's lecture notes. I'll talk about those a little bit, and feel free to ask questions. Any questions you like in the chat. Doesn't have to be related to what I'm talking about and stuff like that, because remember, it'll take a little time for it to show up for me and respond to it. So just jump in with questions in the chat. And also, if you could just give me a hi or a thumbs up in the chat so that I know that folks are watching. I know I can see that it says we've got about 10 folks that are connected here and stuff like that. But just say hi in the chat to sort of build a little bit of community here, so I know that y'all are listening and watching and that sort of stuff. So the stream will go for about an hour today, and then I'll keep going until all your questions are answered, I guess. Hey, Molson, good to see you. So that gives you a sense about how long the delay is between my seeing it and then you seeing it. So there's a little bit of delay, as you can see. Hi, Josh. Okay, so let's talk a little bit about standing waves. You've been working on your lab this week. Hi, Lucas. Hi, Kayla. Hi, Julia. Hi, everybody. Good to see folks online and paying attention here too. So let's talk a little bit about standing waves, then on strings, and then I'll extend it to material on standing waves in sound tubes. And so I'm going to use very sophisticated paint software over here to sort of draw and give you a sense. This is sort of like my whiteboard, I guess. But so the situation with standing waves on strings is that, so let's say we have a situation kind of like what we had in the lab, and you saw some of it. You could sort of see what was going on in the videos there. So let's say I've got a fixed end of the string right here, and I attach the string to the wall at an anchor point right there, so that the string is it's fixed at that spot. That means that the string cannot move up and down at this particular position there because there's an anchor. But imagine that the other end of the string over here, we're going to wiggle up and down with at a particular rate, a particular frequency. Now, as I described in the lecture notes, what happens if you wiggle a string up and down on this, on this side, the wave pulses that you produce as you wiggle the string up and down are going to travel down the string, and they are going to reach this end of the wall and be reflected back towards the starting point. So what happens when a wave pulse hits the spot and reflects back is there's going to be an inversion of the phase of the wave, which means if I originally started out as a peak, the reflected wave bouncing off of the wall is going to come back as a trough or a valley in the wave. So if I lift it up and then drop it back down to produce a pulse that is above the equilibrium position of the string, say I'll just draw sort of a dashed line here. This is what the string would, I'll put the anchor right there. Make the anchor bigger so we can see it. That's where the string is if I'm just holding it level. If I lift it up and then bring it back down to equilibrium, I'll have a pulse that's above the equilibrium traveling down, hitting the wall, but then the wave pulse that reflects back will be underneath that and will travel underneath back towards my hand. Now here's the thing. If I don't just create one wave pulse, if I wiggle the string up, down, at a steady rate, at a particular frequency, then the wave pulses, then as they bounce off of the wall, are going to come back and eventually get back to where my hand was wiggling the string. Now here's the thing. If my hand happens to be at the low point in my motion of the string up and down, when the reflected, inverted wave pulse reaches that spot, then I have sort of two pulses adding together at the same spot on the string to produce a larger waveform. But remember, it requires that the travel time to go down the string and back has to be exactly equal to the time that it takes me to complete an oscillation to go all the way, to complete half an oscillation and to go all the way back down. So in other words, if the rate at which I'm wiggling the string exactly matches the time that it takes for the waveform to go down to one end and back on the string, then I get this effect called resonance. That frequency is just the right, natural, perfect frequency to build up a steady wave pattern where the string, instead of just having all these tiny little wiggles traveling down the string, it reinforces this very specific wave shape and sets up a situation where the whole string travels up, the whole string travels down, and that's what we call a standing wave pattern. Okay, so the conditions for the standing wave pattern then are that, for instance, that if there's a node at this end, and remember, a node is a position on the string that doesn't travel up and down. If it's such that the wavelength occurs, I'm going to draw the string now. Let's be a little bit more circumspect. There we go. There's our waveform. Let's say it does that. So this is half of a wavelength, right? This is just one peak. It hasn't gone underneath at all. This is one half of a wavelength. And if this distance from here to from the oscillator to the wall, the anchor point, is L, then in terms of the length of the string between the oscillator and the wall, if that's L, then the wavelength is, see, this is half a wavelength, so one half of a wavelength is the same as the length of the string. In other words, this implies that the wavelength is equal to twice the length of the string. And notice that puts a node at this spot right here and a node at this spot right here. So the waveform would have this particular shape. And this corresponds to the longest wavelength that you could possibly have to achieve this resonance phenomena, where there's constructive interference between the waves that are continually being produced as I wiggle the string and the reflected waves that are bouncing back towards it, that continually reinforce one another to produce constructive interference. So that's the longest wavelength that you can have. If the wavelength was, say, 3L, then notice that there wouldn't be a node between, I'm not at the equilibrium point here at this end and that end. If it was 3L, then I can't fit that waveform on our string perfectly. Okay, so Juntao is asking why the wave is half of the length. It's because it has to do with how fast I'm wiggling the string. So remember, we have this expression right here. Lambda times F is equal to the wave speed. Okay? The wave speed depends on whatever the tension in the string is, which that is whatever it is. We're stuck with that. And then it also depends on the density, the linear density of the string. So I'm stuck with whatever velocity of waves there are in the string. How fast do the wave pulses travel down the string? Notice what happens if I start with a really low frequency. The wavelengths are going to be really long. So if I have a low frequency, that corresponds to a big wavelength, because lambda times F always has to be equal to V, whatever V happens to be for that string. Now if I start with a really low frequency, then the wiggles that I send down the string won't reinforce themselves because they won't have the right wavelength, and they won't have the right timing for the reflected waves to add up with the waves that I continually produce by wiggling the string. If I slowly speed up how rapidly I wiggle the string, what that does is it shortens the wavelength because lambda times f has to be v the whole time. So if I increase the frequency, eventually I will get to a wavelength that is exactly equal to twice the length of the string. So by increasing the frequency, I shorten the wavelength, and eventually I get the right wavelength to produce this wave pattern where I get constructive interference between my waves I'm sending out and the waves that are coming back at me. Hopefully that answers your question, Juntao. If it doesn't, just write it in the chat again. I know it's a little bit annoying with the delay, but hopefully that's a good explanation. It works. Let me know if it's okay or if it needs more. So eventually I get this situation where lambda is exactly equal to 2L, and that produces this waveform. You're welcome. Glad it helped. So it produces this waveform, and this is only what really it looks like, of course, is it looks like kind of, you can see the whole string kind of going up and down, and this is a situation where the whole string goes up and down like this, the standing waveform for the lowest possible frequency. So this is, I've started with a really low frequency and it doesn't do it, it just produces little wiggles in the string, and then eventually I get it fast enough where lambda is equal to 2L, and it produces this really big, really big sort of simple wavelength. Oh, hello. So that's the situation there. Notice then that the frequency for which this is going to occur, and this is the first frequency that it happens for, so I'm going to label it with a 1. That happens when the frequency is V over 2L. Okay? So that happens when V is over to 2L. So notice I've used this expression here. I said V, the frequency is V over the wavelength, the wave speed, whatever that happens to be for that string, which has to do with its tension and its mass per unit length, and then divide by the wavelength, which we just found out up here that the wavelength that produces this waveform is twice the length of the string. So there it is. It's V over 2L. Now we could break this out a little bit. We could say it's 1 over 2L. All right, just a second. I have a... All right. Okay, 1 over 2L. Did something pop up on my computer that I don't want to pop up right now. Okay, times the wave speed, which remember that is equal to the tension over the mass per unit length. So this expression with the radical here is our V. Okay, so that does it. Okay, so Juntao is asking you a good question here that I just saw in the chat. Yes, it has to do with the timing. Notice how the wavelength is 2L in length because that's the distance it has to travel back to get to the point where it's reinforcing the waveform that I'm producing at this other end of the string where I'm wiggling. So I'm wiggling this end of the string right here, and notice 2L is that distance that it has to travel down to get back to where it was, to interfere. Okay, so I'm measuring L and I'm saying the longer the string, the more time it has, the more time it's going to take to complete the travel down and back. So the length of the string does matter, and that's how the frequency ends up having to do with that length. Okay, so then the question becomes, all right, well, what's next? Well, what if I wiggle the string a little bit faster? Well, if I wiggle the string a little bit faster than this particular timing, then I won't have complete constructive interference between the new waveform that gets produced and the one that's being reflected back at me. It totally will screw up the timing. Well, it won't totally screw it up, but it'll definitely mess it up so that I don't get perfect interference any longer. And there's little bit of a problem. It's gonna create a wave pattern on the string, but the amplitude, the size of it's not going to be perfectly constructive interference any longer, and the waveform will get a little bit smaller. You may have noticed this happening in the lab experiment if you've done that already, that like if I add too much tension, I screw up the timing in it, and the waveform got a little bit smaller. And similarly, if I didn't have enough mass on the mass hanger to change the velocity of waves that travel up and down the string, if it wasn't quite right, I didn't get the biggest standing wave pattern because I wasn't getting perfect constructive interference. So you have to have the timing just right. So if I screw up that timing by wiggling a little bit faster than this, I'll get a wave pattern on the string, but it won't be as large and as stable a standing wave pattern as if I was at the perfect frequency. And in fact, if I increase the frequency too much, I might get to the point where the time is exactly wrong, like the wave is going down while I'm heading up, and it will produce a wave pattern where essentially the string is flat. I'm wiggling one end, a little bit at each side, and the middle of the string is hardly moving at all, or not moving at all. That's when we get total destructive interference. But eventually I could get to the point where if I wiggle it fast enough, I also produce a time where I've gone through, instead of going through half a full period, I go through 1.5 full periods of wiggling during the time that it takes for the wave pulse to go down and come back. Now, if that's true, then I'm back at constructive interference again. So by wiggling it faster, I change the wavelength even more. I shift it to be even shorter, because notice how the wavelength, if I wiggle it at a different frequency here, it's got to be the same velocity the whole time. If I wiggle it up and down quicker, the wavelength gets shorter so that the product of the wavelength and the frequency stays the same velocity. So let's have a little bit of a look at that. So let's erase this. Okay, because that particular waveform, we're not going to be producing that waveform anymore on my string. Okay, I'm going to produce a wavelength or a wave that has a higher frequency and therefore a shorter wavelength. And now, imagine that I was to produce a wavelength or a waveform that looked like that. Notice what I have here is that this is actually one full wavelength being produced on the string. One full wavelength now is equal to the length of this, is exactly equal to the length of the string. So I get rid of the half here. And what I find is that the wavelength is exactly equal to the length of the string. Lambda is equal to L in this case. And this corresponds to me wiggling it with a faster frequency. I'm wiggling it, more rapidly. So I'm going to call this F2 because it's the second wavelength that I had, the second waveform that I was able to produce. And notice it's V over L in this case. And notice what I'm going to do here is I'm going to say, well, that's equal to, just to have it sort of in the same form as here, I'm going to say, well, that's 2 over 2L. It's the same thing as, 1 over L, or V over L. But I'm just, I haven't changed the tension in the string. I haven't changed the string's mass per unit length or anything like that. All I've done is change how rapidly I'm wiggling the string. And notice that this is the same sort of expression as this one up here. It's V over L is the frequency now. Now notice that this is twice as big as the top one. It's twice as big. So there's my factor of 2 over 2L times the square root of F over mu, where F is the tension in the string and mu is its mass per unit length. Okay, so then what the string would look like is sort of this, where now I've got two little humps in the string going up and down, and the whole string now is doing this with a node at this end right here where I'm wiggling it, a node exactly in the middle, and a node at the anchor point on the other end, with other parts on the waveform just traveling up and down. Now, that's the next frequency that it works for. And the one that works after, does that make sense? So there have been a couple of questions, but I want to make sure that this makes sense to everyone and how everything is working out. So if I wiggle it twice as fast, I make the wavelength half as big as this expression here for lambda times f equal this wave speed tells us. If frequency doubles, the wavelength gets half as large. And when I do that, I produce a new waveform that has nodes at the ends. But in addition to a node at the end, it has a node in the middle. A spot where the string neither moves up nor down. Now what I also want you to notice here is that this waveform has what we call two antinodes, two spots where the string is traveling with its, as far away from the equilibrium point as possible. So this position right here along the string is called the antinode, and here's another one. Now if we were to do this again, wiggle the string even faster, what we would notice, all right, we'll do this quicker. All right, something like that. So this is our equilibrium point. Now here's where I'm wiggling the string from again. Now see if I can get this right. This one isn't quite so easy to draw, but I'll do my best. That's not bad. If I wiggle the string 3 times faster than the original frequency, then I will get a spot, a position where there are 1, 2, 3 half wavelengths. This is 1.5 wavelengths. 1.5 wavelengths, or 3/2 of a wavelength, is equal to the length of the string. And that means that the wavelength would be 2/3 times L. And this happens for the third frequency. So I'm going to write F3. I guess I'll put it right here. F3, the third frequency in the series that produces this standing wave pattern, which I hope you notice has 1, 2, 3 antinodes with a node at each end and then 2 nodes. One 1/3 of the way, one 2/3 of the way down. F3 then would be equal to, if I solve this expression here, if I solve for the frequency using F is equal to V over lambda, I get 3 over 2L times the wave speed, which is F over mu. And hopefully now you can kind of see the pattern. The pattern is that the frequency that will produce a standing wave is equal to n, where n is the number of antinodes you want to produce, over 2 times the length of the string times the square root of f over mu. So in other words, the frequency for a standing wave pattern that produces n antinodes is equal to n over 2L times the speed of waves as they travel down the string, the square root of f over mu. And that is the general expression then that tells you what frequencies will make a given standing wave pattern. So that's what we were doing in lab last week, or what we were doing in lab, last week through this week. What I was doing is there was a given frequency, and then what I was doing is changing the string tension to change the wave speed, which then allows me, the more tension I put in here, the fewer the number of antinodes for the given frequency of oscillation. It was a little different than what we're talking about here, but it's got to have a little bit of a twist here to make it fun, right? Okay, does that make sense? I'll pause here just to see if there are any questions on this. So if there are no questions, just say, yep, I totally get it. Just put it in the chat, and I'll just wait and answer questions then when I see it, or we'll move on to sound waves in tubes in just a second to make sure that we're all on the same page here. So while I wait for the questions to pop up, if there are any, notice if I increase the frequency here to 4 times the original frequency, I will produce a wave pattern that has 4 antinodes with 3 antinodes in the middle, 3 nodes in the middle, and so on and so forth. So the faster I wiggle the string, the more antinodes I'll get, and the better the more complicated the wave pattern will end up looking. Okay, so it looks like folks are okay with how things are looking here. So what I'm going to do now is move on to how we treat this with sound. It's going to be very similar to the ideas. I'm just trying to clear stuff out here a little bit. Maybe it works. There we go. All right. Give myself a little bit of space to work with, and then we'll talk about standing waves in a tube. Now, so what we're doing when we produce sound, okay, we're going to just talk about just a standard old tube. In a lot of ways, this is a tube sort of in cross section. What we have maybe at one end of the tube is maybe a speaker cone. Okay, so like we have a speaker right here. Okay, this is supposed to be a speaker, and this will oscillate here. This like little speaker cone, it'll like wiggle up, in and out and stuff like that to produce oscillations in the air that we're going to send down the tube. Okay, so we're going to start with a tube that's open at both ends, and we're going to look at how the sound wave can be analyzed. Okay, so when a sound wave then, so what we have here is a sound wave that we can represent either in terms of pressure or in terms of displacement of the waveform. And it's kind of easier to describe one as opposed to the other. So this is what I'm going to do to start with. I'm going to say, let's talk about characterizing the wave in terms of pressure, atmospheric pressure. Okay, now what I want you to remember, and I'm going to put this out here for just a second. So the pressure wave, so the P wave, the pressure wave is 180 degrees out of phase okay, just for a reminder, in a sound wave, the way to represent it is you could use pressure or you could use displacement. The pressure wave and the displacement wave. Sorry, I should put, with the S wave. Okay. Okay. The S wave here being, this is the displacement. And P is pressure. Okay, so you remember that from last week? We said the way to describe sound, we have two different ways to describe it. One is to say when sound is produced, the pressure is oscillating above and below the ambient pressure. The other way to think about it is that the molecules of air are wiggling back and forth like the coils in a spring. And so there's this, you could either say, well, the displacement of air molecules or whatever, of the medium molecules can be used to express the wave, or you could use a P wave, to describe how the pressure varies with position and time. So either one is fine, but recognize that when you use one way to describe the wave, pressure, it's 180 degrees out of phase with, it's 90 degrees out of phase. 90. That's my terrible mistake there. 90 degrees out of phase. Not 180 degrees. 90 degrees out of phase. Terrible mistake there to put 180. 90 degrees out of phase. So what this means is, like if the pressure wave is it looks like a cosine function, then the displacement wave looks like a sine function. They're 90 degrees out of phase with one another. What that means for pressure versus displacement waves in sound, another way to think about it is if you're thinking in terms of standing waves, at the position where the pressure is at a node in the standing wave, the displacement wave is at an antinode. So a node in pressure, that position is the same spot where a displacement antinode would be happening. and vice versa. If pressure was at the antinode spot in the standing waveform, then the displacement would be at a node. Okay, so here's what I'm going to do. What I'm going to do now is I'm going to plot in this tube. I'm putting a dotted line right down the middle. Okay, and down the middle, what I'm going to do is I'm going to plot as a function of position within the tube, and the height now is going to be pressure. Okay? The height is going to be pressure. So, plotted vertically is going to be the pressure. Now, here's the thing. At the spot where I'm at the end, where the tube is open to the outside air, the pressure has to be atmospheric pressure. Okay? It has to be atmospheric pressure. All right. So it's got to be, I know it has to be a node at this spot and a node at this spot. Okay. So what that means is, just like with the standing wave on the string, the pressure wave function, the pressure function, has to be at nodes at the ends, and then in the middle it can be whatever it wants, but it's got to be nodes at the ends. So what I imagine here is taking the speaker and changing the frequency from a really low frequency and just slowly turning it up. And eventually I'll get to a spot, a frequency, where, and this is true, remember this expression is just as true for sound waves and it is for waves on a string, except now we're talking about the velocity of sound waves traveling in air. If I increase the frequency, I shorten the wavelength. If I have, remember, V is about 343 meters per second for standard temperature. If I have a really low frequency, I have a really long wavelength, and I won't get to the point where standing waves would be set up where I have nodes at the ends in pressure. But if I slowly increase the frequency, just like wiggling the string faster in the previous discussion, eventually I'll get to the point where the wavelength is just right to fit into the tube so that there are exactly the length of the tube. That length of the tube is L, just like before. And notice how this is half of a wavelength. So this particular situation where I've changed the frequency to be just right, I'll have nodes in pressure at the end. Okay, I'll have nodes at pressures at the end. Now, what this means is that this frequency, which is the lowest frequency I can get, is equal to V over the wavelength. But let's check the wavelength on this again. The wavelength for this is, well, this is half of a wavelength is equal to L. So the wavelength is, again, equal to 2 times L. And that, again, will be the lowest frequency. But now V is not the square root of F over mu. It's the speed of sound. So the frequency we're talking about that will produce a loud sound with a really big amplitude from constructive interference would be this particular frequency. And then, because that meets the boundary conditions. And if I turn the frequency of the speaker up so that it wiggles faster, produces a higher pitch, I won't hear as loud of a sound any longer because the amplitude will not have been enhanced as much by constructive interference. So if I erase this waveform and get to the point where, again, I'm ready to wiggle the speaker a little bit faster, eventually I'll get to a point where, again, there's a node at each end, but the waveform would look something like this. Alright. Notice how this is exactly one full wavelength inside of the tube again. I have nodes in pressure at the ends because it's open to the outside atmosphere and it needs to be. But this new frequency, again, would produce, but I would have, in order to get that wavelength to be equal to L instead of 2L like it was here, I have to wiggle it twice as fast. So it would be, the frequency would be V over L, which is the same as 2 times 2 times V over 2L. Just to sort of get it right, to make it look sort of like this form here. So I see Juntao has a question. So why is the lowest frequency that amount? If the pipe is wider, the pitch can be higher, and the frequency can be lower. We're assuming that this is a pretty narrow pipe compared to the size of the wavelengths that are involved. So the width of the pipe actually doesn't matter. Remember, this height that I'm showing here inside of the pipe, this width of the pipe here, not the length of the pipe, but the width of the pipe actually doesn't matter. And what I'm plotting here is I'm plotting pressure as a function of distance along the pipe. So don't take this plot here too literally, other than showing how the pressure is varying along the length of the pipe. So the pitch, remember, is whether the note is a high note, versus a low note, low. So that's what we're talking about with regard to pitch and volume. The volume, the pitch is not very much affected by the width of the pipe. It is a tiny little bit, but not too much. It actually is much more affected by the length of the pipe, not its thickness. Okay. Hopefully that answers your question. Let me know if it didn't, Juntao, and I'll go further into it. So then I think you can see that we have the same sort of expression here. If I change this again, if I make the frequency even higher, I shorten the wavelength even more, just like with the wave on the string, and I would find then that I would get something like this. Inside of so now I've got 1.5 wavelengths fits inside of this, so that F is equal to 3 times V over 2L. So that I think you can see the pattern here is the same as the pattern associated with the waves on a string, where it's N times V over 2L. The difference here is that this L is the length of the tube, and then V is the number of is the speed of sound in air that's inside the tube. Okay, so that's for a tube that's open at both ends. All right, any questions on this? Hopefully that's relatively clear. Things are going to get a little bit weirder when we talk about a tube that's closed at one end and open at the other. But for now, if we just look at pressure, it looks kind of the same as we talked about before. All right, so I'll pause here and see if there are any questions. Does that make sense? So we're applying pressure in here. Okay, yep, it's good, or no, it's now good. Let me know. It's okay? Okay. So notice again here the N value that we associated with this. This is equal to the number of antinodes that fit in this. This is what we call a harmonic series. So the first harmonic is the lowest possible frequency that will produce a standing wave inside of this tube. And the second harmonic would be, double that. The third harmonic is triple that. The fourth harmonic would be quadruple that, and so on and so forth. So that's the naming convention that we have here. The integer that multiplies the fundamental frequency, or the first harmonic, names that harmonic. It tells you which harmonic we're talking about in the tube. All right, so let's sort of clear things out here to give us a little bit more space again. And we're going to bring this back into play here about the pressure and the displacement waves. Okay, so let's change the situation a touch now. This sort of will test us a little bit about how things work inside here, inside this tube. Okay, so let's say that instead of a tube that is open at both ends, we close this opposite end here. So the tube isn't just hollow now, it's a tube that is got an end that's closed. Now, in order to produce sound, introduce a disturbance into the tube, one end of a tube always has to be open to make sound. It just has to. So we've got one open end here, and we got a closed end over here. Now, here's the thing about what happens then at this end, and why we're going to use displacement now to describe this wave instead. The reason is that I know that at the end, if I look at air molecules that are at this position right here, way at the right end, the closed end, they can't be displaced to the right. They cannot, because there's a wall right there. They can't go further right than they already are. So the displacement must be a node at this spot, which means it has to be a pressure antinode. So now, instead of plotting the pressure as a function of distance along the tube here, I'm going to plot horizontal displacement on the vertical axis as a function of where we are in the tube. And I know that it has to be 0, the displacement has to be 0 at, exactly on the axis here that I've drawn in dashed lines. It's got to be exactly 0 at this spot. But I know over here on the left-hand side, I have to have a displacement antinode, because that is the side that is open to the atmosphere and must exist at a pressure node. See how we're mixing our ideas of pressure and displacement waves to come to a cohesive way of describing the wave, but we can only describe it using one way at a time. So here's what I know. On the left-hand side, I have to have a pressure node, which according to this statement here is a displacement antinode. And I know, because of the way that the end of the tube works, that I have to have a displacement node at this spot. So if I draw a wave that has this character, I have to have a displacement antinode over here where it's got to be the biggest it possibly can be, and a displacement node over here where it's got to be right at equilibrium. All right, well, what's the lowest or what's the longest wavelength that will do that? I will draw it. This is the waveform that does that. This is a quarter of a wavelength. The length of the tube is equal to 1/4 the wavelength. It's from the peak down to equilibrium. It's not from equilibrium to equilibrium. That's a half of a wavelength. That's the full, it's full half a wavelength. It's from peak to equilibrium. So what does this tell us? This tells us that from this expression right here, the wavelength that we're looking at here, so 1/4 the wavelength is equal to the length of the tube. This implies then that the frequency, or that the wavelength that is produced by oscillating the speaker at just the right frequency, that will produce a standing wave pattern in this tube, the wavelength is 4 times the wavelength. Which tells us then that the frequency for which this will happen. Okay, I'll answer your question on why in the last situation we can't have a quarter of a wavelength in just a second, once I write this one down. Okay, this is V then over 4L. Okay, so this is the frequency. So if I turn the frequency up from really, really low until I get to V over 4L, that's when I'll have a standing wave pattern. Now, Juntao asked just a little bit ago, why in the last situation we can't have a quarter of a wavelength. I'll show you why. Okay, let's say here's the length of our tube. I'll erase this in a second, but okay, the tube is open at both ends. Okay, now what I know, if I plot this as pressure, this one I'm plotting the displacement, but here I'm going to plot pressure. Okay, if it was a quarter of a wavelength in the tube, then it would look something like this, where I have a pressure node, and then I have a pressure antinode here, and a pressure node at this end. Here's the problem, okay? The timing isn't quite right for this. The boundary conditions aren't met. At this end of the tube, the pressure needs to be at equilibrium. It's got to be at zero. It's got to be at the ambient pressure. Because just to the left of this spot inside the tube right here at this spot right here, notice, at this end of the tube, if I go just a little bit further left, it's outside the tube. It's ambient pressure. It's undisturbed air. It can't go from maximally biggest oscillation pressure to zero pressure in no distance. To meet the boundary condition that the pressure oscillation has to be a node at each end, 1/4 of a wavelength doesn't meet that condition. This condition says that I've got to have a displacement antinode here, but on this end I've got to have a displacement node. They've got to be opposite. Whereas this one, since this side of the tube and this side of the tube are the same, the wave has to have the same exact character in both of those spots. It's either got to be all node or all antinode. It can't have one and then the other at the other end because of the symmetry of the situation. Both of these sides of the tube are open. So I can't have one side of the tube behaving completely different than the other side of the tube since both sides of the tube are equivalent. Does that answer your question, Junta? Why a quarter doesn't work in the previous both open end situation? Hopefully that helped. See, this situation I have two different things. I've got a closed end and an open end, so their character has to be 100, since open and closed are 100, they're completely opposite things. Here, I'm making sure that the waveform is doing exactly opposite things at the ends as well. And this one, I can't have that because I've got two ends that are the same. The waveform, whatever it is, better be doing the exact same thing at the ends. Okay, so now let's talk. So the waveform that's produced here would be again a standing wave. But what if I wanted to see what the next standing wave is going to look like? What does the waveform look like in displacement for the next one up? Well, what I need to do, remember, is I have to have a node at this end in displacement. I have to have an antinode at this end. Okay, so what's the next one that does that? Well, the next one that does that will be one that ends here at 0, and then let's see if I can draw this right. This is not quite so easy to draw to make it work exactly right here, but I'll do my best. Okay, so it's going to go something like this. Okay, so not exactly, not perfect, but here is, this is a quarter of a wavelength here, and here's a quarter of a wavelength here, and there's a quarter of a wavelength there. That looks like 3/4 of a wavelength is equal to L. Okay, so notice from equilibrium to the low point is a quarter of a wavelength, and then from this spot here back to equilibrium is not. So this is half of a wavelength here, and then this from here to here. I know it's a little bit distorted, but then from here to here is another quarter of a wavelength. So this is half of a wavelength plus another quarter of a wavelength. So it's 3/4 of a wavelength. So the next frequency produces a wavelength that's 3/4 of. There's 3/4 of a wavelength in L. So for this situation, then I guess I will say this. For this situation here, what I have is that 3/4 of a wavelength is equal to the length of the string, which tells me then that the wavelength is equal to 4/3 L. All right. So if I put this in for my frequency, I get 3/4L times V. All right. Now here's my dilemma. In the past I said, well, in the next one we just call tube. But the reason I really put tube, by this point we're probably sort of thinking to ourselves, well, it's the harmonic, it's the integer that we multiply the base, fundamental frequency to. It's that integer that we multiply by. That's what our label is. But notice that this isn't double. This is triple the original frequency. So I'm not going to label this F2, even though it is the second frequency that is produced. I'm going to label it F3, and then because it's triple this one. This again becomes a harmonic series where I'm multiplying times an integer. I'm multiplying the base frequency times some integer to get the next frequency in the series. So let's just do one more. Okay, let's just do one more, and then we'll sort of see what the situation is. All right, so in this case now, what I'm going to do is again wiggle it faster to shorten the wavelength to get, the exact right shape. So I'll see if I can sort of do this. Okay, so that one I guess I drew kind of okay. All right, so notice I'm going to go sort of backwards here. From here over to here, that's one full wavelength. I've gone from here to here. That's exactly one full oscillation in the displacement function. And then here's another quarter wavelength. So altogether what I have here is 1 1/4 wavelengths is what fits in L. So what I'll do here is just make this relatively simple. I'll just say that is equal to 5/4 of a wavelength. 1 1/4 wavelength is equal to L. So then I say, well, the frequency that would produce that exact right length for the wavelength would be 5V over 4L. So I guess here I've got 1, I got 3, I got 5 times the original frequency, because V over 4L is the original frequency. This says multiply times 5. So for a tube that is open at one end and closed at the other, the frequencies, the harmonics that are produced, the frequencies that will produce standing waves in that tube are NV over 4L. That's one thing that's different from the waves on strings and the tube that's open at both ends, is that the denominator for this one is 4L. But the other thing that is really different about this, extremely different, is that N is an odd integer. Only the odd harmonics are produced. There's no even ends in this. It's 1, 3, 5, and then the next ones would be 7, 9, 11, and so forth. So N is an odd integer for a tube that's open at one end but closed at the other. Okay, so that's how a tube that's open at one end and closed at the other is different than a tube that's open at both ends. Okay, so that's my exposition for today on this. I wanted to make sure that folks understand how these standing waves get produced and sort of why the shapes are the way they are, and then why the frequency that produces a standing wave, why those work out to be the way that they are. And hopefully this clears things up. If it wasn't clear, it's getting clearer. So while I wait for questions here, because I'm going to give a little bit of an example of how this stuff is interesting in, I don't know if it necessarily is your everyday life, but how there are real life examples that matter here. Okay, so one of the examples that I do in class, and again, I'm just talking a little bit here to kill time while I wait for your questions to come in on this, but I will say this because I think there's sort of an interesting thing to notice about the, oops, I should have just cleared everything. There we go. All right. Let's have a tube that's open at one end or open at both ends. And let's say what I have done is right here at L over 2, I've got a hole in this end right here. All right. So now what we have is a situation where, and this is an example problem that I showed in class, and hopefully you've had a chance to look at it. So if I look at the pressure, okay, let's say that I cover this hole by putting my finger over it. So I've covered this hole, so it's just like this tube is just a tube with no hole in it, okay? If I plot pressure as a function of distance, then this is the fundamental frequency, or this is the situation where I have pressure as a function of distance along the tube. There are nodes at the ends, and there's an antinode in the middle. Okay, and the reason there are pressure nodes at the ends is because these are open to the outside atmosphere, and the pressure has to be ambient, standard atmospheric pressure at those ends. Okay, now, let's say that what you have here is a hollow tube and you're blowing into it. Okay, so this is kind of like a whistle, or you've seen those things, the recorders. Maybe you used them in elementary, middle school or something like that to practice your music class or something like that. You had a recorder. Okay, it's just a tube. It's a hollow tube. It's open at both ends. You blow in it, and when you blow in it, you cause a disturbance that produces this standing waves, produces a particular node of a particular pitch. Now, here's the deal. If you remove your finger from this spot right here, and you open this position at L over 2, half the length of the tube, if you open that position up to the outside air, so this spot right here now, that's open to the outside. Guess what? This wave pattern is no longer allowed. Why not? Because the conditions that allow a standing wave pattern to be set up in here is anywhere, any spot along the length of the tube that is open to the outside air needs to be a pressure node. It must be a node. But this waveform right here has an antinode at that spot, halfway down the tube. That spot, that waveform now, no longer satisfies the conditions that anywhere that's open to the outside atmosphere would have a pressure or a node. Well, what is one that does meet that characteristic? And again, I'll open this up. Open this up at right at L over 2, right at halfway down the tube. I've got this hole in it. Well, that waveform doesn't work. The first harmonic, the fundamental frequency, doesn't work. But what does? Oh, I should draw the equilibrium position here down the middle. Okay, what does? This one does. Notice that this waveform has nodes at the ends, but also oops, I don't have it exactly at the right spot. Just imagine that I've drawn this way better. There we go. That's a little bit better. Okay. Notice that this has a node at exactly the spot where this is open to the outside atmosphere. So by removing your finger, you change and blowing into this thing to produce sound that goes into it, the sound that results will be the sound associated with the second harmonic. The second harmonic is now being produced inside of this tube, and the pitch goes up. So by putting your finger over the hole in the middle, I produce this note of this particular pitch, this frequency. Remove your finger from that, and it changes the pitch that you would hear when you blow noise into it. You just blow air into this tube. Normally you would say fundamental frequency, that is the note, that is the pitch that is heard. The lowest possible, the lowest possible n value that you can have. That doesn't work here. The n equals 1 doesn't work, but n equals 2 does. And so this note is what you hear. Does that make sense? So why different notes on a recorder come from different fingerings is that you're covering, so you cut holes in the top of in the recorder, and then you cover them all with your fingers and you blow it, and it just produces the fundamental frequency. But if you open certain holes, you change the frequencies that will be played by the recorder, that are allowed to be played by the recorder when you blow into it, and you can play different notes with different fingerings. So this is the basics of music, from instruments that look kind of like a tube, like the recorder, the clarinet, the flute, the trombone. Everyone knows what the trombone is, right? That one actually, to play different notes, what do? You're actually changing the length of the tube, because that slide is part of a curved tube. If you change the length of the tube, you change the frequency of the fundamental frequency that you get. So all of these sound waves in tubes, they're all the basis of music. Now there are other instruments. Again, not every instrument is like a tube that's open at both ends, or open at one end and closed at the other. They're not like an organ. The organ, like the organ that you play like this. That's tubes that are open at one end, closed at the other. Interestingly enough, and then what happens is air just blows into the tube, and then the tube makes noise. It makes a particular note, and which tube you blow the air in. That's why you got these big pipe organs, which the length of the tube that you blow air across corresponds to which key you're pushing on the keyboard, and it produces a different note. Piano works completely different. Yes, it's a keyboard, but what the keyboard is doing is hammering strings. Well, that's just waves on a string. There are different lengths, different thicknesses, different tensions, and all that sort of stuff. And how a piano tuner tunes a piano, like the homework talked about, is by changing the tension of the string. Guitar, I got one back there. Guitar string, you play different notes by pressing the string to the fretboard to change the length of the string. The higher the shorter the string, the higher up on the fretboard you press the string to the board, the higher the note will be. Okay, so basically all of musical instruments come about from standing wave resonance in tubes and in strings, for the most part. Percussion's a little bit different, but you can do that. Are there any questions on this? I went off on the music tangent of things just to give folks a real life way of thinking about how these things work, but also to give you a chance to ask questions if you wanted, but no one asked any. So maybe it's super clear and you just wanted to hear all the, you're just hanging on my every word. I doubt that that's it. I hope it's at least interesting and useful to you. Are there any questions that I can answer about how these things work? I'm going to do a quick look at the lecture notes to see that I've kind of covered the main themes of what I wanted to talk about today, but feel free, ask any questions in the chat that you want about how this is all working. I'm going to check to make sure that the lecture notes were kind of, see if there was a main topic I wanted to talk about. Let's see. Sound, timbre we talked about. We had standing waves. Oh, there was beat frequency, I suppose. Did folks want to hear a little bit about the idea of beat frequency and that sort of stuff? Again, it has musical connotations or implications, but I just want to make sure that folks are getting the information that they want from this. I know it's not super interactive, but this format allows me to sort of convey what I was trying to get across in the lecture notes. So I'll ask now then, and I'll just wait for a response on it. Do folks want me to talk about interference in time and the idea of beat frequency, or are you done? You've had enough. It's been over an hour, and you're good to go, and we can stop. Up to you. Just tell me in the chat whether you want me to go on with that or not, and I'll sort of clear stuff out here to make space for myself. Okay, so Lucas is saying, "Yep, let's see the idea of beat frequency." Let's see if I can find something interesting here. Okay, I'll talk really briefly about the idea of beat frequency. It's a little bit hard to visualize, but I wanted to make it, especially when things are static. Let's see. So Juntao is asking, I want to ask, so for the spring in the very beginning, why spring can go back? Are we certain that the time of it go? I don't quite understand the question. I think you probably mean the spring or the string. I was trying to talk about a string in the beginning when we were, why spring can go back. So what we're doing, just hopefully this will clarify it. I'm kind of trying to interpret your question here because I don't fully understand, but I hope I do. I think I do. So what's going on with the string in the beginning is, oh, no problem. Okay, then it makes sense to me. So you're holding onto the string at one end, and let's see if I can. Let me see. I'll try to bring something into this that's a little bit more. Maybe we can see this. Okay. So hopefully you can see this. So this is the University of Colorado has a nice little demonstrate thing here, and what I'm talking about here is if I've got a fixed end over here on the C clamp, so this is stuck. It's kind of like the anchor point that I talked about, and in this I can wiggle this up and down. So this is the string. It's basically a string of beads here, so you can kind of see how things look. And then if I wiggle this, I'm just talking about taking the string and wiggling it up and down. Now if I wiggle this notice what happens if I wiggle it faster. Notice how the wavelength gets shorter. Okay. So, and if I wiggle it slow, notice how the wavelength is really long. Okay? So, that was what I was talking about before. It's like if I grab onto this end of the string and I wiggle it at a particular rate, if I get just the right rate, I can set up a standing wave pattern, which I'm actually kind of close to doing right here. It's not perfect, but there's sort of a standing wave pattern that's being set up here with maybe like 4 antinodes or something like that. And that's sort of what I was talking about doing. Like I can wiggle the string at a particular rate up and down, and then I can wiggle it. I can either wiggle it slow, or I can wiggle it faster, or I can wiggle it really fast. And by changing the wiggle, I change the length of the wave, the wavelength, the size of the pulses, and that can affect what then whether I'm at resonance or not at resonance. Does that help? It's just if I wiggle it faster, then yes. So the frequency. So I'm going to relate this then to waveform stuff that we talked about last week. The period of the oscillation that I'm wiggling the string would be the time that it takes for me to go all the way up, all the way down, and then back up. That's one full oscillation. So I start in the middle, I go up, I go all the way down, and I come back to the middle. That's one full oscillation. That would be T, capital T, the period. The frequency is the reciprocal of that. So if it takes me let's say it takes me a quarter of a second to go all the way up and all the way up, all the way down, and then back to the middle. If that takes me a quarter of a second, then I complete 4 oscillations per second. Okay? So then the question or the comment you have is, so the lowest frequency is 1 up and 1 down, so the wavelength is 2L. Yes, that would be right. Exactly. That's exactly right. Okay, other questions? Okay, so we could do the mathematics of beat frequency, or we could do the, I think I'll sort of describe what beat frequency is just in general. Let's say that I have 2 sounds. This is what I tried to describe in the lecture notes, and I don't know the degree to which it's clear. I hope it is, but I just want to go over it just a touch, because that's one of the other main factors. Okay, So let's say that I have an axis here where, oh, give myself something to draw with. Oops. There we go. Now we're drawing. Okay, so this is an axis right here, and let's say that I have a particular waveform, and this is height of the wave. This is a sound wave. So let's say it's, I don't know, it's pressure at a particular position. So let's say I've got a position over here that I'm listening to a sound at a particular spot, and then this is going to be time. So let's say that I create an oscillation, and there we go. There's a certain time between peaks, which would be then the period. So this is the time between peaks. So this is a particular frequency of sound wave. It's the pressure's oscillating at a particular rate. Okay. Now, so that's one of my, that's one sound wave. Let's say I also have a second sound wave. This one oscillates more rapidly. Okay? This is higher frequency. It's a shorter time between peaks. Okay. Just want to make sure. So are we back? There was a little bit of a hiccup with my system here, but hopefully we're back and doing stuff. It said my streaming software had a little bit of trouble. So hopefully we're not buffered or anything like that at this stage. So as I was saying, I said that this waveform has a particular frequency associated with it. If you turn this speaker on, you would hear a particular pitch. If you then turn this one off and stood with a different speaker putting out this different sound wave, notice the time between peaks is shorter, the frequency is higher. Okay? If you turn that one on, you would hear a pitch that was higher pitch. Okay? So I've got now one pitch or the other. What if I played each signal through a different speaker and played them at the same time and listened to the sound that I heard? Well, what I would do, the sound that I would hear would be the combination of these two sound waves put together. So what I would do is I would say, all right, I would take these two sound waves and superimpose them on top of one another. So I guess I'll put the brown wave here, something like this. I'll try to kind of oops, I wanted to be brown. It's like the one here. Okay, so something like this. All right, not exactly what I had before, but something somewhat close. Now, what I would have to do then to figure out, well, what is the sound wave that is being the total sound wave of these two sounds put together? What would I have to do? Well, what I would have to do is I would have to say, what's the brown plus the black at every point in time along here? What's the brown value plus the black value? Now, this isn't going to be exactly right because, well, this is way too messy to do for real. But if I had two frequencies that are relatively close together, what I would have is something like this. I would start out with an amplitude which maybe the two amplitudes are, like here, it shows where I'm at a peak with the black wave, I'm at a trough with the brown wave. What does that mean? That means that those two waves at that particular moment are canceling, destructive interference. But notice that down the pike here, I've got the black wave and the brown wave both at their peak, both exactly lining up. Well, that would mean they get constructive interference. So what happens is the following. The waveform, the actual waveform that you would hear is the combination of these two waveforms, and you would have something like, maybe something like this. Where I have, and I'm going to sort of draw, I'm trying to use all the colors, but notice how the amplitude gets big, and then the amplitude gets small, and then the amplitude gets big, and then the amplitude gets small. So what you would end up having then is a situation where the amplitude determines how loud the sound appears. It determines the volume of the sound. At this moment here, and this moment here, and this moment here, the amplitudes are all pretty close to zero, which we would say is extremely quiet. At this spot here, where at the moments when the waves are at points of constructive interference, where their peaks happen to line up exactly right with one another, now I get an amplitude of the resulting sound which is very large. That would appear to be loud. So what you get is this warbling effect, where you hear a sound that kind of goes whoa, 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 whoa. It gets louder, then quieter, then louder, then quieter. You've got this oscillation in the amplitude. Now what you hear is a frequency which is equal to the average of the two frequencies of the black and the brown wave, with a volume that also oscillates. So if I have a pitch of 200 hertz and another pitch of 220 hertz, by the way, that's relatively a low note. 200 hertz is a pretty low note. The 200 hertz and the 220 hertz sound, when you combine them, the pitch that your ears would perceive as it tries to disentangle that complicated combination of the two, the pitch that your ears would hear is actually the average of the two. It would say, that sounds like a 210 hertz sound to me. But it's a 210 hertz sound whose volume warbles, whose volume oscillates with a frequency equal to the difference between the two. So the rate at which the amplitude oscillates is equal to the difference between the two. So if I had frequency 1 was 200 hertz and frequency 2 was 220 hertz, then the perceived frequency, I'm going to put that as P, the perceived frequency would be the average of these two. It's 220 hertz, or sorry, 210 hertz. But this frequency would oscillate in amplitude with something that's called the beat frequency, which is the difference between the two. And it's the absolute value of the difference, because you can't have a negative frequency. It would say here that this thing would oscillate 20 times a second in volume. That's 20 hertz. That's terrible. It's a terrible H. To fix it. Fix the whole thing. There, that's good. So that's what happens when I have two frequencies of sound put together that are close to one another. The perceived frequency of the two would be the average, and then the beat frequency tells you the rate at which the amplitude, which has to do with the volume of the sound, how rapidly that oscillates. This is so. As I wait for questions here, so please go ahead and ask questions. As I wait for questions, I'll give you another sort of real-world example of how this is useful and works. One example of this is in tuning, and it is in a homework problem. But I will use it with the guitar, and I could do it with my guitar. I'm thinking about it. My guitar is out of tune right now, so it doesn't work. But the idea is the following: if you play a note on your guitar and you compare it to a reference note. So let's say I want to tune the note, a particular string, to A. Okay, so the note A is 440 hertz. If I pluck that string, if I have a reference frequency, if I listen to it, okay, to a reference frequency, like I have a tuning fork that always plays 440 hertz. When I tap the tuning fork, it plays a pure note of 440 hertz. If then I play my guitar string and it's at 443 hertz, so it's not exactly in tune, then what will I hear? I will hear an oscillation in the volume. I'll hear whoa, 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 whoa. 3 times per second it'll warble. Because when I play the two notes together, they don't exactly match. So there will be a beat frequency where the sounds will come into alternatively constructive and destructive and alternate because of the timing effect. Now what I would do then is I'd say, well, you're too high, you're sharp. I'm at 443 hertz and it should be at 440. So what I can do is I can lower the tension in my guitar string, which lowers the frequency of oscillation of the guitar string, because I'm decreasing the speed of waves in the string. Now when I do that, lower the tension in the string, maybe it goes down, maybe I tune it so it's at 441 hertz instead of 440. Then what will I hear? I will hear whoa, 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 whoa. I will hear the notes with a beat frequency of 1 hertz. Lower it a little bit more, and I'll get to the point where the combined sound produces no beats. That means that there is no difference. There is zero difference between the standard tuning fork frequency and the frequency of my guitar string. So using the beat frequency as a reference to, as long as you've got a reference frequency to compare to, you can use it to tune instruments or tune anything where you want the frequency to match up. Another application for this is in laser tubes and stuff like that, where you can get phase locking and frequency matching and that sort of stuff. You can use the beat frequency, but this would be light that's got beat frequency, because laser light is turns out it's waves, as we'll talk about later in the term. But this has applications for tuning all sorts of things, from tuning the radio waves that come to your television antenna or your cell phone or something like that, to tuning musical instruments, anything that you want to tune to. This effect is useful for tuning, because you just change the frequency of the thing you're trying to tune until the beat frequency disappears and becomes zero, because the beat frequency always is the difference between the two frequencies that are involved with one another. Okay, so questions on this? I didn't see any questions pop up. I think we can probably call it if there are no further questions, because I know it's been an hour, 20 minutes now, and it's been a long time. But hopefully you've found it useful. But I do want to make sure any questions before I call it, I want to make sure that I get to all your questions answered. So I'm going to clear this out. Wait for questions to pop up in the chat. If you don't have any questions, just say no questions, and then we can just call it. Lucas has got a question. So Lucas is asking, what about different tuning, different frequencies at the same note, like tuning an E string to an E string? Okay, so those are different. They differ by an octave. Tuning the beat frequency is really only strongly perceptible if the frequencies are relatively close to one another. The frequencies between excuse me, the difference in frequency between one, a middle E and a high E are so large that we'd be talking about hundreds of hertz difference, and that would be basically, it would be a frequency that is a beat frequency that is so rapid that it wouldn't be perceptible to human hearing. So while the beat frequency is happening, there's sort of a destruction of the ability to really perceive it by human ears. Notice also that the reason why that average and the difference thing works is because the frequencies are hard to distinguish for human ears. The effect still happens, but it's very much harder to perceive. So that's why you don't really hear the effect between an E and an E. There's two different values of the same note on the scales, is because you can perceive them as two distinct notes rather than seeing that they're kind of almost close to the same note, and I'm just seeing an oscillation between the two. You can distinguish them with your ear. That's why you don't really perceive the beat frequency with frequencies that are very far different from one another. Okay? So if folks are sort of out of questions or out of gas or whatever, because I know I'm sort of running low on this too, but I want to make sure I answer all your questions before we call it a day. But go ahead and ask them if you got them. Oh, yes, I did want that. I did want to make note of that, and I know this at the end. I should have probably mentioned it at the beginning, but I'll put it in an announcement as well here in a little bit. You bet, Lucas, no problem. The way I want quizzes submitted is I would really rather that folks submit their homework quizzes just typing the answers in. I had considerable trouble. I had some folks that did submit their quizzes tried to put them as pictures, and sort of as I predicted, some of them worked, but most of them didn't. And I know some folks sent their homework work in emails, attached to emails, but that ends up getting. I get a lot of emails, so it's really hard for me to look back and find the things as I'm trying to grade stuff. So strongly suggest that you put your homework, just type it into the text box there rather than trying to attach a picture or something like that. Just a couple sentences describing what you did, 2-3 sentences, just describe what you did is good enough. If you do a calculation, kind of show me. If you want to use the equation editor, you're welcome to do it, but you don't have to if it's costing you a lot of effort and time. If I wasn't able to read what folks put in their quiz this last homework, I did give a 0 and explain on that particular one, but I'm willing to accept your work if you send it to me via email. If you tried to put something in and you got graded 0 on it or really low on it or something like that because I couldn't see it, just send it to me and I'll fix it. But the only grade I could assign to it if I couldn't see it was 0. That's the only thing that I could do. But I will accept it and fix it later if you do send me your email. Send me an email what your work was. With either as a PDF or a picture that you can attach to email. But as I mentioned in the beginning, in the introductory announcement with homework, D2L does not play very well with uploading pictures and stuff like that. I would say about 1/4 of the time it works. So you don't want to be in that 75% where it doesn't work. So just type it in. Just type it. That is my suggestion. Other questions that I can answer before we call it a day here. So we do have the exam coming up on Friday. This week I did shorten it up a little bit. Normally in class we would have had the exam probably on Wednesday and started new material on Thursday. But just because we're still getting used to all this, I decided let's just take it a little bit easy. I'll just do 3 weeks, 3 days worth of lecture this week, and then we'll have the exam on Friday and Saturday. And so we're a little bit short on material this week, but I'm fine with it as long as folks are feeling like they're able to keep up and all that sort of stuff. Juntal asked for the quiz, how many multiple choice and how many? Okay, so for the exam, I assume that you're asking about, the exam will be 10 multiple choice questions, so just standard multiple choice questions, and then there'll be 3 calculational problems that you'll do, and you'll have 2 hours to complete the exam once you start. You can start anytime between Friday at 8 a.m. and Saturday at midnight, 11:59 p.m. But once you start, you'll have 2 hours to complete it. You got to get it done in 2 hours. You have 120 minutes. So pace yourself on it. Make sure that you get through it okay on that. Okay. Any other questions that I can... Hopefully that answered Juntal's question. And Andrew's question on homework quizzes and stuff. Hopefully lab is going okay. So the next lab will be on sound produced in tubes. Okay. Oh, Christian's got a question. Can I quickly go over an outline of what you want on the lab? Discussion, analysis, and so on. So Christian, yep, you're welcome, Juntal. Christian, the way to look at it is, what I would suggest is to look carefully at the lab report format that I put in the, it's in the under content and material. So if you go to material content, laboratory, there are 2 files in there right now. One is the lab report format. Follow that format. The other thing that's in there is the actual Lab 1 lab handout that tells you kind of how to do the lab. So if you go to that lab report format, it tells you, the outline is, I want you to tell me the purpose, the procedure that we used, which, okay, tell me kind of how I did it. And then there's data and analysis, data and calculation section. So that's 3 sections so far. And the 4th one is the conclusion. So and it tells you how the points are broken down. I think it's 2 points. Oh, I can't remember what it is. 2 points, 4 points, 6 points, 4 points, something like that. I don't remember what it is. But it's 20 points total. But it says in the format actually what the different point values are. Maybe it's 2, 6, 8, 4, something like that. Anyway, the most of it is going to be in that lab report format. So give me your purpose, tell me the procedure, the step-by-step instructions, then give me your data, calculation and analysis, and then a conclusion, which refers back to the purpose and discusses the quality of your results and any uncertainties or challenges that you encountered. So that's what I want there. And then just submit it as a Word document for the assignment that is listed as Lab 1, which is coming up to be due in about 12 and a half hours or so. Something like that. And then there'll be a new lab out then tomorrow morning for sound waves and tubes. Speed of sound measured by that. Any other questions that I can answer? So Thursday, we'll have a Zoom meeting. Rather than this, we'll have a Zoom meeting that pops up Thursday morning at 10 a.m. Again, let me know on the discussion boards if timing could be better, if we could do a different time for these things. But hopefully this is useful. The Zoom meeting will have basically, we'll be able to go a little bit easier, go back and forth on questions and stuff. But also it's going to be sort of a review for the exam that's coming up on Friday. So I would expect that homework questions and questions on exam topics and stuff like that are going to be really heavily emphasized then on Thursday with the exam coming up the next day. So come with your questions. So start studying now. I would say start studying on Wednesday and stuff like that. Get through your material as soon as you can. I would really strongly suggest trying to get your homework done sometime in the next day or two, or at least make a good attempt at it so that you can be ready to ask questions on that homework on Thursday morning's Zoom meeting. Because if you're waiting until Thursday afternoon or Thursday night to do that homework, or even waiting until after the exam, it's not going to do you as much good as if you'd done it beforehand and tried to so that it can help you on the exam that opens up on Friday, Saturday. Yes, you can wait for your homework to do on Sunday night, but that ain't going to do you any good for the exam that you would that's going to have to be finished by Saturday night. So get in early on that homework if you can. I would put in the work tonight and tomorrow if at all possible, and get that stuff done as quick as you can, or at least get to the point where you could ask a question on it. So I would look at every one of those homework problems, whether you've gone through the material or not, and get some questions at least in your head that you can get answered then on Thursday. Andrew's got a question. Is homework time bound as the exam is? No, it's not. No, it is not. Once you start the homework, it's unlimited. You can. There's no time limit on the homework. So once you open a homework quiz, you have as long as you want to complete it. Of course, it has to be done before the due date on Saturday, but yeah, you could open it on Monday and not complete it till Wednesday as long as it stays open. But if you have an internet glitch or something like that, that's the problem with that. But you could take 3-4 hours on homework if you want. You could sit there for 6 hours and have it open, and it's no problem. It's just there's a default suggested time of, I think, an hour or 2 hours or something like that, but it's not enforced. Homework you can take as long as you want. Other questions? All right. If there are no other questions, then you're welcome, Andrew. Then I think we're going to call it at this point. We've been over an hour and a half. Hopefully this has been useful to you, and you've been able to sort of see some of the stuff that's coming up and interesting. We will see you on Thursday for sure, but I'll keep an eye out on things. Just to let folks know, I've gotten through about 3/4 to 7/8 of the homework. I will have the rest of the homework graded today. You can go and look at your feedback on those. So if you go back and look at your various attempts, you can then look at the feedback that was left at each one of those attempts. So there's a little notice. So if you got something completely right, don't expect any feedback. Just, there's just an implied thumbs up if you got all the points. If you lost a point or two or three or something like that on a homework question, then there's almost certainly feedback left unless it was left blank by you. So if you made a little mistake in your thinking or something like that, then it'll be there. So I'll answer all questions. That it looks like folks are out of questions, but I think I'll call it there, and we'll just look forward to seeing you on Thursday. Get that homework done. We'll see you then.